Okay, good morning. Let's begin. First, I'm going to share the screen. And then let me grab my chat to make sure I see what people are writing. And guess what is our next step? Our next step is toss the coin. Okay. Quiz it is. So today we're going to have a quiz. So that you know, you'll have to write, so prepare. You will have to have a piece of paper, a pencil. You will have to write a proof because it's about 5.1 and 5.2 and 5.3. So you probably can guess there's going to be a nice proof out there. And then what you need to do is you'll have to take a picture of your proof and upload it. Okay, so for one question, you need to upload. Make sure to have it. Questions? How many questions? There is only one question. It's a proof writing. You should have plenty of time to do it. You have 20 minutes. You probably do not need more than 10. Some of you probably do not need more than 5. But again, there is plenty of time. Write it all down. I want to see all the steps. Don't miss any words you're supposed to be saying. I want to see the assumptions. I want to see you know how to do the induction proof. Okay? It's not a hard quiz. It's like, as I said, just we did similar problems. We did something similar in discussion too. It's closed book, closed text, but try to do everything, put everything you know out there and submit. You have till 9 p.m. today to take the quiz. Okay? Great. So let's see. We have been talking about binomial. So we talked about binomial theorem, and we are going to talk about how we can use it. So as a reminder, the binomial theorem tells you how to expand x plus y to the power n. So it tells you that x plus y to the power n is going to be the summation of j goes from 0 to n, big J from n, x to the power n minus j, y to the power j. We did discuss that in this case, n minus j plus j is just n. So you always have terms so that the powers of both terms add up to the same number n all the time. I gave you an example of how to expand x plus y cubed. And then I also talked to you how to find the term of x plus y to the 24, for example. Give me the term 10. And then, so in this case, we said, what if 10 is equal to j? What is going to be the coefficient? The 10th coefficient is 10 out of 24. However, some of the questions are not going to have an exact form of x plus y. Instead, in this case, my x is x, but my y is positive 3, correct? Because it's plus y. Yes, so 3 positive. And I want to know the coefficient of x5. How can I do it? Well, in this case, I will have x to the power 5 and y to the power 5. So in this case, my y is equal to 3, correct? So my term for the coefficient of x5 is going to look like that, right? So what is going to be my coefficient of x to the power 5? The definition of coefficient is a number, correct? The front of x to the power 5. And in this case, the number is this whole 10 choose 5 multiply 3 to the power 5. So this whole thing is your coefficient. And now let's talk about some corollaries. So I'm saying directly from binomial theorem, I can get, so corollary is something you can really get as a result from theorem pretty easily. I'm saying somehow from my binomial theorem, I can say that if I have a summation from k equals 0 to n, k choose n, I'm saying this sum is actually equivalent to the 2 to the power n. Now, I'm saying it comes directly from that theorem. Question, how did we get it? So how those two actually connected? Why am I saying it's the same? Well, let's look. So we have x plus y to the power n is summation of j equal to 0 and j n x n minus j y j. How those two are similar? Well, what I want you to look at is how those two are connected. So we definitely can see that this portion here looks identical to this portion here, correct? Agreed? Yes. But then I have x to the power n minus j and y to the power j. And in here on top, I don't really have anything like this, correct? But we know a couple of things. What can you tell me about 1 to the power x? How much is 1 to the power x? It's always 1. So let's look at this summation again. Do you agree that this one is equivalent to what I have on top? Because 1 to the power n minus k is 1, and 1 to the power k is 1, correct? So it's literally like writing nothing. But what does it mean going backwards? It means that my x is 1 and my y is 1, correct? And we said this is the formula I can use, correct? So I'm using it with x equal 1 and y equal 1. So what do I get? Well, I get 1 plus 1 to the power n, which is 2 to the power n. Do you see how you can get this corollary directly out of the binomial theorem? Yeah, now let's try it again. Let's see if this time you can get the trick yourself. I am saying -1 to the power k, kn is equal to 0. How did we get that? So pretty much, again, you need to figure out how I can take it to the binomial form. So in this case, if you look at my binomial over here, I have y to the power k, correct? I know that my y is equal to -1, right? What is going to be my x? X is going to be 1 again, correct? Because I can kind of say this is equivalent and then using binomial theorem, what we get is we get 1 plus -1 to the power n. But how much is 1 plus -1? Works like a magic. Okay, I have one more for you. And your thing is going to tell me what are going to be again my x and y. And let's kind of give them maybe numbers. Like that. So, okay, my sum is getting more and more ugly. Here we go. Just a reminder, the actual letters are not really matter. I can change n to be m, I can change k to be j, I can change it however I want. So can you guess how much is that? Well, here, Trevor is suggesting we're going to have y is equal to what? Y is easy because it's already here, correct? Because we have 2 to the power k, right? So what is my y? My y must be true, 2, correct. Now the question is, what is my x? X is 1, correct? Because it's missing. The only thing I can replace it, I cannot replace it with -2 to the power n minus k, because -2 to the power n minus k is not always 1. And right now I don't have anything here. So my x must be 1. And now let's plug it into the formula. What are we going to get? 1 plus 2, correct, to the power n. And hence, as Trevor said and Evan said, we have 3 to the power n. Great. So this is how you can play with those formulas and get a lot of interesting identities. And those of you who take Calc 2, for example, you're going to learn a lot about sums and conversions. A lot of it comes directly from this binomial theorem. Now, another thing I want to talk about is called Pascal's identity. Pascal's identity says that k to the power n plus 1 is equal to that. Yes, Trevor, you're right. If y can be whatever I want, if x is 1, then I get a lot of different y plus 1s to the power n, correct? So I can get 2 to the power n, 3 to the power n, 4 to the power n, 10 to the power n, and so on using those type of formulas. That's correct. So now we are going to talk about Pascal's triangle. And moreover, I'm not really going to talk about it. I'm going to show you a video. Um,
of numbers, but it's actually a math. This may look like a neatly arranged stack of numbers, but it's actually a mathematical treasure trove. Indian mathematicians called it the staircase of Mount Meru. In Iran, it's the Khayyam Triangle, and in China, it's Yang-Wei's Triangle. To much of the Western world, it's known as Pascal's Triangle, after French mathematician Blaise Pascal, which seems a bit unfair since he was clearly late to the party, but he still had a lot to contribute. So what is it about this that has so intrigued mathematicians the world over? In short, it's full of patterns and secrets. First and foremost, there's the pattern that generates it. Start with 1 and imagine invisible zeros on either side of it. Add them together in pairs and you'll generate the next row. Now do that again and again. Keep going and you'll wind up with something like this. Though really Pascal's triangle goes on infinitely. Now, each row corresponds to what's called the coefficients of a binomial expansion of the form x plus y raised to the n, where n is the number of the row, and we start counting from 0. So if you make n equal 2 and expand it, you get x squared plus 2xy plus y squared. The coefficients, or numbers in front of the variables, are the same as the numbers in that row of Pascal's triangle. You'll see the same thing with n equals 3, which expands to this. So the triangle is a quick and easy way to look up all of these coefficients. But there's much more. For example, add up the numbers in each row, and you'll get successive powers of 2. Or in a given row, treat each number as part of a decimal expansion. In other words, row 2 is 1 times 1 plus 2 times 10 plus 1 times 100. You get 121, which is 11 squared. And take a look at what happens when you do the same thing to row 6. It adds up to 1,771,561, which is 11 to the 6th, and so on. There are also geometric applications. Look at the diagonals. The first two aren't very interesting, all ones, and then the positive integers, also known as natural numbers. But the numbers in the next diagonal are called the triangular numbers, because if you take that many dots, you can stack them into equilateral triangles. The next diagonal has the tetrahedral numbers, because similarly, you can stack that many spheres into tetrahedra. Or how about this? Shade in all of the odd numbers. It doesn't look like much when the triangle's small, but if you add thousands of rows, you get a fractal known as Sierpinski's triangle. This triangle isn't just a mathematical work of art. It's also quite useful, especially when it comes to probability and calculations in the domain of combinatorics. Say you want to have 5 children and would like to know the probability of having your dream family of 3 girls and 2 boys. In the binomial expansion, that corresponds to girl plus boy to the 5th power. So we look at the row 5, where the first number corresponds to 5 girls and the last corresponds to 5 boys. The third number is what we're looking for, 10 out of the sum of all the possibilities in the row. So 10 over 32, or 31.25%. Or if you're randomly picking a 5-player basketball team out of a group of 12 friends, how many possible groups of 5 are there? In combinatoric terms, this problem would be phrased as 12 choose 5 and could be calculated with this formula. Or you could just look at the 6th element of row 12 on the triangle and get your answer. The patterns in Pascal's triangle are a testament to the elegantly interwoven fabric of mathematics, and it's still revealing fresh secrets to this day. For example, mathematicians recently discovered a way to expand it to these kinds of polynomials. What might we find next? Well, that's up to you.
Okay, so, okay, now you can hear me, right?
Can you hear me? All good? Okay, great. Sorry, I'm moving from microphone to speakers when I'm trying to show you the video. So it's like interestingly going back and forward. So this is as far as Pascal's identity. And you can now connect it really to your to the Pascal's triangle, because this is exactly what it is. Remember how when he generated the triangle, he said we add. So 1 plus 0 is 1, 1 plus 0 is 1, right? And then we did 0 plus 1 is 1, and 1 plus 1 is 2, and 1 plus 0 is 1 again, correct? But if you think about it, those are already my coefficients, correct? Because here I choose 0 from 2 plus 1 out of 2 plus. So this is my 1 choose 2, correct? So now if we add them together, we're going to get the 3, which is actually going to be 1 choose 3. And so on. So that's really kind of the Pascal's identity helps you to generate Pascal's triangle. Okay. So here is what we're going to do. First, I'm going to give you your homework from section 6.4. And it is going to be 2b, 4, 7, 12b, and 16. Second of all, I'm going to remind you that we are going to have our next test, not this coming Monday, but the Monday after. So our next test is November 1st. We are like about 1 week before it. And again, we are going to have our review section in the morning of that day. So on Monday, November the 1st, we're going to have review session, and then you're going to have test at 6:30 p.m. And now we're going to finalize our chapter 6 with kind of like something in between group work and discussion of the whole class. So what we're going to do is I'm going to give you a couple of problems, and we're going to try and attempt them and discuss it. And I probably will send you to break rooms for a little while, like random break rooms, to discuss how do you think you should solve those problems. And then we're going to talk about solutions. So number 1 is going to be this. We have a witness of hit and run. And he tells the police that license, of the car had 3 letters followed by 3 digits. He tells us it starts with AS. And has digit 1 and 2. Only once. Okay, so he remembers there was 1, 1 and 1, 2. He doesn't remember where they stand. He remembers it starts with AS, but he doesn't remember anything else. So this is what he was able to catch as the car was driving by. The question is, how many license plates police needs to check? This is your question number 1. Your question number 2. How many different arrangements of 8 people to sit at a round table? Consider same if can be obtained by rotation. So pretty much I have a table out here, and assume I only have, I don't know, 3 people. So person A, B, C. The rotation of A, B, C is still considered the same because I still have the same neighbors. Okay, everybody still has the same number. So this is the same rotation for me. Because A has C to the right and B to the left. So same rotation. Now, B, A, C is not the same because A has B to the right of it and C to the left of it, which is different from where B had A to the right and C to the left. Wait. Okay. B has C to the right, A to the left in green, and B has A to the right and C to the left in the other one. They are not the same. So A and A. Come on. Sorry, my computer is not the best today or internet connection or whatever. I don't know why I'm fighting it so badly. Well, it's not the same. Okay, sorry. It does. Here we go. Now it writes. Great. Okay. Do you understand both questions? Yep. So on that beautiful note, I am going to pause recording. So when you come back, you scream at me, but we need to unpause it. Okay? So I'm pausing the recording. Yes, I started the recording. Thank you for reminding me. Okay, how did it go? Do we have solutions for both questions or one question? Okay, let's start with question 1. So for question 1, we had 6 spaces. We knew it starts with AS, and we also knew we should have someplace here, we should have 1 and 2, correct? So what did we get for the first one? Bring me your numbers. Okay. So here is how we can do it. We can say it like this. So this one is easy. We know there are 26 options of how to pick this letter here, correct? We definitely know there's 26 letters we can put here. Now, what we can do next is we can say, okay, I need to find a space for my 1, correct? Because I need to place 1 someplace, agreed? So I have 26 multiply. In how many ways can I pick space for 1? And then in how many ways can I pick a space for 2? So after I place 1, how many spaces I have left? 2 spaces. So I need to place 2 inside one of those spaces, correct? So now I placed my 2. And finally, after that, I do not have a space to pick, but I have an empty cell someplace out there. And I need to put numbers there. How many numbers are possible? 8, because we said 1 and 2 do not repeat, correct? So it cannot be any number between 10. It must be a number between 8. Now, if I am going to say 1 and 2 can repeat, saying 10 here is not going to be correct because you're going to be double counting things. An example is going to be, so I place 1 here, and then I place 2 here, and then, for example, I decide 1 is out here. This is the same as saying I place 1 here, I place 2, and then pick 1 for that one. And you count it twice, correct, in this case, if you put 10. So it's much more complicated if you're allowed 1 and 2. I'll let you think about it till Monday and come up with a solution for if I can repeat 1 and 2, how much more complicated it is. So you'll have to separate it differently. But pretty much in here, what we really have is pick letter, place 1, place 2, pick number, cannot be 1 or 2. And now let's talk about second problem. In a second problem, I have people sitting in a round, correct? And I don't remember how many I gave you. 8. 8 people sitting. 1, 2, 3, 4, 5, 6. Yes, lovely. So we have 8 people we need to sit. First, let's change the problem. Assume I need to put them into the line. Yes? In how many ways can I do it in a line? Okay, hopefully we all know this is 8 factorial. This is easy. So pretty much if you think about it, I can kind of use the same approach. I can say, I need to find somebody who is going to be sitting here. And then somebody who is going to be sitting here with 7 options, 6, 5, 4, 3, 2, 1. The issue is this combination is going to repeat, correct? This combination is going to be the same if I'll rotate it by 1, for example, correct? So how many same rotations I have? So how many rotations which are equivalent to this rotation I have? 8, correct? So pretty much for every of 8 of factorial rotations, 8 of them are always going to be the same. So I must divide by it because every like 8 combinations are bad. So the correct answer is 7 factorial. This is your correct answer. Okay, great. So now let's summarize what we did in chapter 6. In chapter 6, we talked about counting, but we talked a little bit more about it. We talked about how can we do things in different ways, correct? And we had lots of rules and we learned how to choose things from. And we also discussed that it's important to know if the order matters or order doesn't matter, correct? So there are tons of different things and ways of doing it. So Now, we're going to give it a name. Generally, this whole thing we did right now, it's kind of combinatorics. So the name for it is combinatorics. The chapter 6 was about combinatorics. In those cases, we calculated in how many different ways we can do something. So we literally like kind of counted, and our numbers were pretty big, correct? Because this 26 multiply 3 multiply 2 multiply 8 is actually going to be a huge number, correct? So this is an important thing to remember. When I ask you to say in how many different ways you can do things, generally the answer is a number, a large positive number, correct? It cannot be negative number. It's always positive number. In a chapter 7, we are going to be talking about probability, okay? And probability is going to be different. Probability has a property that it always must be in between 0 and 1. On the test next Monday, you're going to have both combinatorics and probability. I want you to remember that you'll need to read the question really carefully and understand which one you need. Because the most common mistake is after I cover probability, every question I ask after that, students try to give me probability. But I do not always ask for probability because right now we only talked about combinations, correct? So we will continue on the test. I will also have some combination questions too. Don't try to put it into probability. Read the question carefully, okay? It might be a little bit confusing. Now, in order to understand probability, you must first understand the combinatorics. And the reason for it is in probability is calculating how many cases are good cases for me, and then divide them by all possible cases. This is what is always going to give me probability. So in order to do it, I first need to count my options. So you cannot do probability without combinatorics. Does it make sense? So we will define probability as number of situations I like and work for me divided by number of possible situations. And how do you count the situations? You use rules we studied in chapter 6. Okay? Now, on that note, we are done for today. Don't forget to do the quiz. It's still 9. Don't forget to submit your discussion, and don't forget to join a group for discussion. I still have some people who forget every once in a while to join the group. It makes it so much harder for us to grade. So please, please, please join groups. Have a good day, great weekend, and I'll see you on Monday. Bye.